0.050 mole per dm cube of potassium hydroxide, the pH. Solution. Okay, we have potassium hydroxide, ionizes to give us potassium plus OH negative. 1 mole of base is equal to 1 mole of base. 0.050 mole of base will give us X. The hydroxide ion concentration would be 0.050 mole per dm cube. So this is the hydroxide ion concentration. Now remember, that the product of base and base is equal to 10 raised to the minus 14. So, if that's the case, we've gotten this, we want to get this, because they say the pH. So, this will therefore become, please, let me take over the other side. Okay, now this will therefore become 10 raised to the minus 14 over, what is that guy? Over 0.050, which is that of hydroxide. Okay, this is the same thing as 10 raised to the minus 14 over 5 times 10 raised to the power minus 2. So this is, I'm making some of the powers here. So I have 10 raised to the minus 14 plus 2. Let's just put it like that over 5. Okay, sir. Have a nice time. And this is 10 raised to the power minus 12 over 5, and which is equals to, I'm trying to get that of hydrogen ion, not the pH. So now, 10 raised to the power of minus 1, 2 divided by 5 is 2 times 10 raised to the power minus 13. So 2 times 10 raised to the power minus 13 mole per dm cube. This becomes the hydrogen ion concentration. Okay, having gotten the hydrogen ion concentration, we'll proceed to get our pH. Now I'm back here. Now, pH is equal to the negative logarithm of hydrogen ion concentration, which is minus log, open bracket, 2 times 10 raised to the minus 13, which is equals to 2 times 10 raised to the power of minus 13, close bracket, 12.7 approximately, 12.7 as the pH, which shows that it is alkaline in nature. That was our C. Let's look at the D. Yeah, that was C. Now D says that we should calculate the hydrogen ion concentration and hydroxide ion concentration in a solution with pH of 5 and pH of 1.55. With pH of 5, we'll calculate these two. With the pH of 1.55, we'll calculate the two. Let's start. Okay, D. with pH of 5.0, the hydrogen ion concentration will become what? We say that solution pH is equals to the negative log of hydrogen ion concentration. So if the pH is 5, this is equal to minus log of hydrogen ion concentration. Divide both sides by the minus. So minus 5 is equal to log of hydrogen ion concentration. We look for the antilog of both sides. When we do that, we now have hydrogen ion concentration equals to antilog of both sides. Of both sides, hydrogen ion concentration becomes the antilog of minus 5, and hydrogen ion concentration is equals to what? So in the antilog we have second function log minus 5, 1.0 times 10 raised to the power minus 5, 1.0 times 10 raised to the power minus 5 mole per dm cube. So when the pH is 5, the hydrogen ion concentration is this, and the hydrogen ion concentration becomes what? This other one. We say that this, the product of these two guys, is equal to 10 raised to the minus 14. I have this, so I make use of this. So the concentration of the hydroxide ion is equal to 10 raised to the minus 14 over 10 raised to the power minus 5. So this is equal to 10 raised to the power minus 14 plus 5 is 10 raised to the power minus 9 mole per dm cube. When the pH is 5, the hydroxide ion concentration is 10 raised to the minus 5. The hydrogen ion concentration is 10 raised to the minus 5. The hydrogen ion concentration equals to 10 raised to the minus 9. Then, for when the pH is 1.55, we should find the hydrogen ion and hydroxide ion as required. Well, I don't know. Do we have more? We should. Okay, let's take that one as a test. That's our test, our assignment. So you deal with that. Now the question again, let me repeat. If the pH of a solution is 1.55, find the hydrogen ion concentration and hydroxide ion concentration. That is your test. So, question number 8. Okay, let's take 8 too as another test so that we can go into pH without time. What is the pH? Question number 8, which is test number 2, to test to see if you understand what we'll be dealing with. What is the pH of a solution whose hydrogen ion concentration is 3.2 times 10 raised to the minus 4 mole per dm cube? Excuse me. Repeat. What is the pH of a solution whose hydrogen ion concentration is 3.2 times 10 raised to the minus 4 mole per dm cube? I think that one is direct. So let's go to pOH concept. Let me take this out. pOH is the measure of the degree of alkalinity of a substance. Measure of the concentration of what? Or we can say is the measure of the concentration of hydroxide ions in a solution. Now, like pH, POH, remember we say pH is the negative log of hydrogen ion concentration. Now, POH is equals to the negative log of hydroxide ion concentration. So, just like the opposite. pH is the negative logarithm of hydrogen ion concentration. POH is the negative logarithm of hydroxide ion concentration. Now, for any dilute solution, POH plus pH is equals to 14. For any dilute solution, POH plus pH is equals to 14. You have to remember that our pH scale cut across 1 to 14. And that pH scale covers the area of acidity and alkalinity. Alright? So if that is true, this is what we use as our cardinal focus in dealing with POH. Don't forget that. In the dilute solution, this is real. We use this. But pH is this. Don't forget. So let's take our first question. What is the hydroxide ion concentration in the solution of POH of 5.55? Just like in the solution of pH. Alright? So, what is the hydroxide ion concentration in the solution of POH 5.55? Let's say that POH is equals to 5.55. What is the hydroxide ion concentration? Solution. We say that POH is equals to the negative logarithm of hydroxide ion concentration. Now, if the POH is 5.5, what is this? So we can now substitute this. 5.55 is equals to the negative log of OH negative. Yeah. So I want to bring this to this side. I have minus log OH minus, it's equals to 5.55. Divide this up, multiply through by minus 1. I will have log OH negative here. It's equals to minus 5.55. How do I get rid of this? Look for the anti-log. Both sides. So OH, the concentration of OH negative here is equals to the anti-log of minus 5.55. And that is equals to this. Let's check. (2.8 times 10, 2.82 times 10 raised to minus 6. 2.82 times 10 raised to minus 6. More per DNQ, sorry. The unit is important. That's our first solution. Wait, okay, that's not all. B, what is the hydrogen ion concentration in the same solution? So we've gotten the hydrogen ion concentration. So what is the hydrogen ion concentration? We'll bring that law. Remember this. Remember that the concentration of hydrogen ion concentration and the hydroxide ion is equal to 10 raised to minus 1/4. I've gotten this. So I'm looking for this. Hydrogen plus, this is 2.82 times 10 raised to minus 6 is equals to 10 raised to minus 1/4. If I make this the subject, let's cross over it. So my hydrogen ion concentration is equals to 10 raised to minus 1/4 over 2.82 times 10 raised to minus 6. This is equals to 10 raised to minus 1/4 plus 6, okay, over 2.82. So this is 10 raised to the power minus 8 over 2.82. That is equals to what? Let's see. Now, 10 raised to the power minus 8 divided by 2.82. 3.55. 3.55. This is equals to 3.55 times 10 raised to the power minus 9 mole per dm cube. Okay, yeah, we're good. Now let's move on to question number 2. Question number 2 says, a glass cup of orange juice is found to have a pOH of 11.40. Calculate the concentration of the hydrogen ions in the juice. So we've gotten our pOH. Let's clean the board. Okay, let's take the question again. A glass cup of orange juice is found to have a pOH of this. Question number 2. A pOH of 11.40. Calculate the concentration of the hydrogen ions in the juice. Of hydrogen ion. Okay. To find the concentration of the hydrogen ion, we must know what our pH is. From pH, we can get our hydrogen ion concentration, of course. We remember that. So here we say, in every dilute solution, we say pOH plus pH is equals to 14. And now, pH is equals to 14 minus 11.40. Our pH is equals to 14 minus 11.4 is 2.6. So pH is 2.6. If pH is 2.6, we say that pH is equals to the negative logarithm of hydrogen ion concentration. Okay, now, and the pH is this, so this becomes 2.6 is equals to minus log of hydrogen ion concentration. So if I divide this, multiply through by minus 1, I have minus 2.6 is equals to log of hydrogen ion concentration. So over here, I have log of hydrogen ion concentration is equals to minus 2.6. Look for the antilog. Both sides. So I have hydrogen ion concentration is equals to the antilog of minus 2.6. Then hydrogen ion concentration is equals to that. Second function log minus 2.6. 2.51 times 10 raised to the power minus 3. 2.51 times 10 raised to the power minus 3 mole per dm cube. So that is the hydrogen ion concentration. That's question number 2. Okay. Let's take question number 3. We should calculate. Let me see. Whoa. Okay, let's go. We should calculate A, concentration of hydrozonium ion in 0.025 mole per dn cube of aqueous solution of HCl. B, pH and pOH of solution in A above. Okay, let's start with A. Calculate the board first. Question 3. Calculate A, concentration of hydrogen ion in 0.025 of HCl. HCl, 0.025 mole per dn cube. They say we should calculate, that's what is given. We should calculate the hydrogen ion or hydrozonium ion concentration. So to do that, solution. Solution, now I have HCl, ionizes dots to give us this plus this. 1 mole of this give us 1 mole of this. 0.025 of that will give us X. So my hydrogen ion concentration is equal to 0.025 mole per dn cube. That's A. B, the pH and pH of the solution. Okay, let's start with pH. This is A. B, the pH and pOH. pH is equal to the negative log of hydrogen ion concentration. We've gotten the hydrogen ion concentration, so I can just put this minus log of, this is bracket, 0.025, which is equal to, I want to get my pH. So that is minus log, open bracket, 0.025, close the bracket, is equal to 1.60. The pH is 1.60 of HCl. Now the pOH. Alright, Bi. The pOH therefore is what? Solution. Remember we say dilute solutions, in dilute solution our pOH plus pH is equal to 14. We have our pH, so pOH is equal to 14 minus pH, and this is 14 minus 1.60, and this is 14 minus 1.6 is equal to 12.4. 12.4. Okay. I think that was question 3. 12.4. Okay, good. Let's take one more before we go dive into another assignment. An orange juice is found to have a pOH of 9.5. Okay. What is the hydrogen ion concentration in the juice? Let's clean the board first. An orange juice is found to have a pOH of 9.5. So pOH of the orange juice is 9.5. So we should calculate the hydrogen ion concentration in the juice. Okay. The hydrogen ion concentration is solution. We say pH plus pOH is equal to 14. And pH is equal to 14 minus pOH, which is 9.5, and this is equal to 14 minus 9.5 minus 9.5 is 4.5. 4.5. That's the pH now. I want to get the negative logarithm. No, the hydrogen ion concentration. We say that pH is equal to the negative log of hydrogen ion concentration. So let's cross over there. And the pH is 4.5. So I have 4.5 is equals to minus log of hydrogen ion concentration. So if I switch side, minus log of hydrogen ion concentration is equal to 4.5. Multiply through by minus 1, I have log hydrogen ion concentration is equal to minus 4.5. How to get rid of this log? Look for the anti-log both sides. Anti-log both sides. I have the hydrogen ion concentration is equal to the anti-log of minus 4.5, and that is equal to second function log minus 4.5. Okay. 3.16 times 10 raised to the minus 5. 3.16 times 10 raised to the minus 5 mole per dm cube. So that's what we get. Okay. Let's take another test question to see if we understand what we're doing. Test question says, 1A says, what is the hydroxide ion concentration in a solution of POH? 3. B, what is the hydrozonium ion concentration in the same solution in A above? So, number 2 question. What is the pH of a solution whose hydroxide ion concentration is 4 times 10 raised to the minus 4 mole per dm cube? So, you do that, then let's advance. We say the pKa of an acid is the pH at which the protonated and unprotonated species are present at equal concentrations. The protonated and unprotonated are present in equal concentrations. Let's take an acid, for example, ROCOOH, reversibly ionized to give us ROCOO negative plus hydrogen positive. This is the protonated and unprotonated. When this amount are in equal solution, we call that the pKa. Now, if we were to get the dissociation constant of this Ka, our Ka is equal to the concentration of our ROCOO negative and hydrogen ion all over the concentration of ROCOOH. So the Ka, which is the dissociation constant. Since the numeric, look above, numeric values of Ka for weak acids, of course, that is the carboxylic acid, and negative exponential number, we therefore express Ka as pKa, where okay. Let me take the other side. Where pKa is equals to minus log of Ka. We're going to somewhere, we're trying to derive something. Note that pKa is related to Ka as pH is related to hydroxide ion. The stronger the acid, the lower is its pKa value. Hence, Ka is equal to the concentration of hydroxide ion, which is minus log Ka minus log hydroxide ion concentration, which is equals to my pKa is equals to pH. So in this sense, say that pKa is equivalent to pH. Now, because of this, we're going to show how can we derive the Henderson-Hasselbalch equation, which is a cardinal equation which we use in this whole thing. Now, a weak acid HA ionizes as follows. A weak acid HA ionizes as follows. Yeah, what do you want? No. Oh, no. That's far away.
Thank you.
Yeah. Okay. Where do we start? Okay. It ionizes as follows. So if that is the case, we first of all start with our equilibrium constant. Our equilibrium constant Ka will be the concentration of hydrogen and A negative all over Ha. Now we cross multiply when we cross multiply, we have our H concentration of that and that of A is equals to the Ka and Ha here. Now we divide both sides by the term of A negative. Divide both sides by this. We will now have H plus is equals to Ka Ha over A negative. Okay. Having divided both sides, we'll introduce log to both sides. So I now have log Ha positive is equals to the log of Ka open bracket Ha over A. Now I will expand this. I will now have log H positive here is equals to the log of Ka plus the log of Ha over that of A negative. Okay, now how do we get this from here to here? In the laws of logarithm, it says that the log of, let's put it this way, the log of AB, if you want to expand that, it becomes the log of A plus the log of B. Laws of logarithm. If you go through it, that should be the multiplication law of logarithm. So these two, multiplying them or opening them, this is what you get. So if that is correct, we introduce multiply through by minus multiply through with minus 1. So I will now have minus log H positive is equals to minus log Ke minus log HA over A negative. Okay, we know when you get here, minus log this, sorry, let me clean this up. Minus log this is what? Is pH. So I have pH is equals to minus log Ka is pKa. pKa minus log, what's that guy? HA over A negative. Now, the inverse of this, if I turn it over, it changes this to plus. And now I have my pH is equals to pKa plus log concentration of A over HA. This is our Anderson-Hessenberg formula. And that's that. So, with these, we do a lot of things with it, but today we're not going to be discussing the application of these. We just have to understand how pH and pKa, the Ka, the saturation constant, how they are related and interwoven, and in a whole lot of calculations to come, you see that we use these in dealing with that a whole lot. And this goes to a long way to tell us about the strength of acids. Where we talk about buffer substances which resist changes when a little quantity of acid or base is being added into solution. That has to do, goes with the weak acid, or other call them the amino acid too. So, but here today, this is what we have. So we've been able to derive our Henderson-Hessenberg equation in relation to our pH and pKa and so on and so forth. So we stop here for today. Thank you.